Section 3.2 is kind of the cousin to something we did earlier this semester, the intermediate value theorem. And now we're on the mean value theorem, which is in some ways an equivalent when we talk about derivatives. So the mean value theorem, if you remember the intermediate value theorem, it was where we took a point and we said there exists a solution. This is another one, but in this case, we have the function being differentiable. You can make it where it's only continuous at the two endpoints, but differentiable is the really important part of this definition. A little bit side note, I've worked with the AP exam a few times, and the AP exam thinks that continuous is the important property, and they teach their teachers this, and so the AP teachers hammer this home. They're all wrong. They don't, I feel like they don't really understand the principle of the mean value theorem. Differentiable is the important part of the mean value theorem. But you're allowed to restrict that just a little bit on the endpoints. Okay, sorry, monologue over. I really like the AP exam. They do a very good job. Okay, but anyway, if it's differentiable, then there must be some value c such that this equation is equal. And so let's compare these two, and what are we really saying? This, f prime of c, is the slope of a tangent line versus this, which is the slope of a secant line. So if I were to think of this problem, what this problem is saying in graphical terms is that if I have some sort of graph, say I've got a graph that looks something like this, that there's a, sorry, if I have a graph that looks like this, there's a secant line right here that if I take that secant line and kind of move it, kind of move it over, I hit some tangent, some point on the tangent line that has the same slope as that secant line. And if I draw it, if I draw it well, it looks even better. But you can see that at some point on this line, there has to be a spot that has the same slope as that secant line. And you notice because the tangents start too small and then they end up too big. So somewhere in the middle, we hit that sweet spot where we get the same tangent line. Okay, so this theorem just says that there has to be a solution somewhere in the middle. So for example, if we were to look at, say, the square root of x, which has a graph that looks something like this, you might say, what is the slope of the secant line? F of b minus f of a over b minus a. And for this problem, that f of b minus f of a over b minus a is equal to, well, f of b is 2, f of a was 0, because this point is x equals 2, y equals 4, and this point over here is 0, 0. And then the bottom, b is 4, and a is 0, so you notice the slope of this secant line is 1/2, right? That has slope equal to 1/2. Well, what the mean value theorem says is this. The mean value theorem says there must be some point in between 0 and 4. We don't know which point it is, but there must be some point in the middle here that also has a slope equal to 1/2. And that point we're going to call C, and then that slope of that line is going to be f prime of c. So all the mean value theorem says is that there must be a point somewhere that has that slope on it. Okay, this is a theoretical section, so it's not one of the sections we're going to spend a lot of time on, but I think it's important that you see the mean value theorem, that you know that it exists. I'll let you look at those homework assignments, and there's only 3, and you can turn them in. And basically, they all say the same thing. You find the slope of the secant line and say there must exist a point in the middle where the derivative is equal to that point. This also will show up at the end of the semester when we start talking about why the big theorem from calculus, the fundamental theorem of calculus, works. So, this is intended to be a very short, very quick section, and then we'll move on to section 3.3, which is one of my favorite sections in the book.